Hi, today I am going to discuss about chopper fed DC drive. Basically, four types of converters are there depending upon the available input voltage AC or DC and the converter output voltage based on the type of the motor DC or AC. Here we will discuss about DC motors. If the input voltage is AC, then to run that motor, AC is to be converted to DC. Now AC can be converted to DC using controlled or uncontrolled rectifier. In controlled rectifier, we have some option by controlling the firing angle of the thyristors or by controlling the switching pulses of MOSFET, IGBT or transistor. We can control the DC output voltage of the converter. Ultimately, we are able to control the DC input to the motor and then we can control the speed. More about these converters has been discussed in power electronics module. Let's see those things. Here, basically four types of converters are there: AC to DC, DC to DC, DC to AC, AC to AC. This AC to AC will be used in case of induction motor or AC motors. This one also will be used in AC motors. But these two converters will be used for DC motors. Now, this is AC to DC, nothing but rectifier, controlled or uncontrolled. This DC to DC is nothing but chopper. Input is DC, output is variable DC. So, in both the case, output is DC and we can feed across DC motor. So, in this class, we will focus on AC to DC converter. And next class, we will go for this one. This is nothing but a DC series motor. To control the input of this DC series motor, here this arrangement is done. It is nothing but a transformer. Primary winding is connected across AC supply and the secondary winding is connected to this rectifier. So this is uncontrolled rectifier, means only diodes are connected. Then input AC, output DC we will get. But this output is not smooth. So to make that output voltage smooth DC voltage, this filter arrangement is done. Here only one inductor is shown, but in some cases inductor along with a capacitor in parallel also used, or alone capacitor can serve the purpose. Now how we will control the DC output voltage? Now to control the DC output voltage, as these are uncontrolled switches, so we have to control the input voltage. Now this input voltage can be controlled using this tappings of the secondary windings. So if the tapping is at this position, then maximum secondary voltage is applied across this one, and if the tapping is at this position, then minimum voltage will be there across this one. So the AC output voltage or secondary side voltage is controlled to control the DC output voltage. Ultimately, the speed of the motor is controlled. We have seen using various equations that if the input voltage of the DC motor is controlled, then we can control the speed of the motor. So this complete system is nothing but a transformer and uncontrolled rectifier control. So ultimately, just change the tapping of this secondary winding as per the requirement or speed of the motor. So this is the traditional way, but nowadays there are lots of options available. Here we can use controlled rectifier, no need to use this converter. In some cases, if isolation is required, isolation between the AC input and the AC input to the rectifier, then transformer can be used in that, and those transformers are 1:1 turns ratio transformer. That means whatever input voltage we are giving across the primary winding, same output voltage we will get from the secondary winding, but we will get isolation of the source from the load side. This is generally done to or just for safety purpose, isolation between the source and load, so that any fault in the load side should not affect our grid or input source. Let's see what are the other available options. Here it is, controlled rectifier. Now these are thyristors. In place of thyristor, we can use transistor, MOSFET, IGBT, GTU, etc. other switches also. Now for high frequency application, generally MOSFET is preferred, but MOSFET is not suitable for high power applications. For medium power application and medium switching frequency around 20 kHz, IGBT is preferred. But for high power application, thyristor is the only suitable device. That's why here thyristor is shown. Now the firing pulses, these gate pulses of these thyristors are controlled to control the output voltage. So it is controlled rectification. Input is AC, output is DC. This is a separately excited DC motor. Now in this case, this field winding is connected to a separate DC source, and we are controlling the armature current or the armature voltage to control the speed of the motor. How this AC is converted to DC, we can see that thyristor number 1 and thyristor number 3 will be on during positive half cycle, and in case of negative half cycle, 2 and 4 will be on. So in both the half cycle, you will see that current will always flow in this direction. In the negative half cycle, current will flow in this direction. This and back to this. So DC output voltage we will get, and we have control over this DC output voltage by controlling the on period of these thyristors. So these two will be on at a time, and these two in the negative half cycle. Now in case of inductive load, we know that if the firing angle is more than 90 degree, then the output voltage will be negative. Negative means here it is negative, here it is positive. And if the firing angle is less than 90 degree, then we will get positive output voltage or positive DC output voltage. So here it will be positive, here negative. That's why this we can see current is always positive, but voltage is positive in first quadrant and voltage is negative in this fourth quadrant. So two quadrant operation is possible using this fully controlled rectifier. Now let's see. This is your half controlled rectifier. The naming half controlled is because that in place of 4 diodes, only 2 diodes are replaced by thyristors. That means 2 uncontrolled switches are replaced by controlled switches. That's why the naming is half controlled rectifier. Now here we will control the firing angle of thyristor number 1 in the positive half cycle, and diode is automatically, it is forward bias. So in the positive half cycle, current will flow in this direction. Now in the negative half cycle, we will control the firing angle of this thyristor. So negative half cycle means here it will be negative, here it is positive. So when here it is positive, that means it is favorable condition for this diode D2. So 1 and this D1, that means this thyristor and this diode will be off. Then in the negative half cycle, current will flow in this direction. This, then back to this. Now one thing you can observe here, that compared to the previous circuit, here only one quadrant operation is possible. The reason behind it is that when thyristor number 1 is off, then what will happen, as this is an inductor, so this inductor will change its polarity, and upper part will be negative and bottom is positive. Then in that case, what happens, this positive voltage will forward bias this diode D1 and diode D2 also. So the current will flow in this direction. when switch number 1 is off. That means these two diode gets forward bias and the stored energy across this inductor is revealed through these two diodes. And when these two diodes are on, at that time voltage becomes 0. It becomes a short circuit of the motor. So the voltage is 0. That's why this case we are getting. Current is positive still, but voltage is 0. So in no case you will get negative output voltage. So negative output voltage or the fourth quadrant operation is not possible using this kind of converter. Same thing will happen in negative up cycle. Here it is negative, here it is positive. Now current will flow in this direction. After that we will switch up this thyristor number 2. Then whatever energy is stored across this inductor, it will release through this diode D1 and D2 again, and it will be short circuited and voltage will be 0. So in no case you will get negative output voltage. That's why it is one quadrant operation only possible using this single phase half controlled rectifier. Similar thing you can see in case of three phase fully controlled rectifier fed DC drives. So here it is separately excited motor. Same thing, separate DC supply is given to this field winding, and we will control the voltage across this armature or current through this armature to control the speed. Now here three phase input voltage is given to this thyristor. Here three top group thyristor and three bottom thyristor. That means total 6 thyristors are there. Now we have to turn on corresponding thyristor which is favorable for conduction based on the input voltage. That means here we can say that suppose out of these 3 input voltages, if this one is more positive than this and this point, then thyristor number 1 can be triggered and it will be on and current will flow in this direction. Similarly, in case of 4, 6 and 2, out of these 3 thyristors, only one will be on. Which one is more negative than this one? Suppose this point and this point. If the negative voltage is more here, then this will be on. So T1 and T2 will be on and current will flow in this direction and positive output voltage you will get. So like this pairing of the thyristors will be there. At a time 2 thyristors will be on, one from the top group, one from the bottom group, to give this positive output voltage, and by controlling the on period of the switches we can control the DC output voltage. Likewise, as we have seen in case of single phase fully controlled rectifier, as it is an inductive load, so if the firing angle is more than 90 degree, then fourth quadrant operation we will get, and if the firing angle is less than 90 degree, then this quadrant operation we will get. So in more detail you will see in power electronics module about this one. Let's proceed. Here it is 3-phase half controlled rectifier with DC drives. The naming is half controlled because that out of these 6 uncontrolled diodes from 3-phase uncontrolled rectifier, only 3 diodes are replaced by controlled switches or thyristor. That's why it is out of 6, 3 is replaced by controlled. That's why it is half controlled. So 3-phase half controlled rectifier. Now here, as we have seen in single phase half controlled rectifier, that fourth quadrant operation is not possible. Here the same thing will be there. So this diode will be forward biased using this thyristor, and it will be short circuited and the negative output voltage we will not get. And here we will control only the firing pulses of these 3 thyristors. So number of components required to control this 3-phase half controlled rectifier is comparatively lesser, because only 3 control is required. 3 driver circuit we have to connect to control the switching pulses. So it is comparatively easier, but fourth quadrant operation is not possible using this one, and current will be always positive, and first quadrant operation is achieved to control the speed of the motor. So in brief we have discussed. So today we have discussed about thyristor fed single phase half controlled, single phase fully controlled, 3-phase half controlled and 3-phase fully controlled rectifier, and the output voltage of those rectifiers are fed to DC motor, maybe separately excited or series motor. And one traditional circuit of voltage controlled using uncontrolled circuit we have seen using different tappings of secondary winding of the transformer. There also we can control the DC output voltage, but that is not the best way. There are high chances of sparking across the secondary winding if the power is very high, or smooth operation is not possible. But nowadays, using power electronic switches, the tappings can be smoothly changed from one position to another position to obtain controlled DC output voltage by controlling the AC input. But in control rectification, we have seen that input voltage is AC, but we are controlling the firing angle of the thyristor to control the DC output voltage, and a corresponding output voltage is fed to the DC motor. In next class, we will see chopper fed DC drive. That means input will be DC, output will be controllable DC, and that we will feed across DC motor. Thank you.